The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody. It is Wednesday, the 14th of October. You're here at Lunch and Learn. Today, as we noted on the list there, Rich is going to be talking about EMG structure and harmonics. For those that were curious, this session is going to be recorded. We're going to keep everybody muted in the beginning until he's done with the formal presentation. Then we'll take a minute or two to get people unmuted if people have questions. Since he and I, or at least I can't see if you type questions into the chat box, that's not for us panelists. We don't ever see those. Just go ahead and wait until he gets done, with the formal presentation, and we'll take questions. Richard, it is all yours. Great topic. Thank
All
you.
right, Rob, thanks. Yeah, I thought it was time to do this topic. I've done presentations on beta and artifact, but I thought it'd be really valuable to drill down deeper because I see on listservs and I hear talking to people I'm consulting and mentoring, they're talking about stuff they hear about EMG or beta or gamma from other workshops, or they read other listservs, and there's a fair amount of sloppiness in our field about a lot of the topics, and there's a lot of the telephone game, and a lot of people are also speculating at workshops or different places, and they're not clear that they're making speculations, or they may not, or they may just be reiterating somebody's speculation and thinking that it's something valid that can be applied. So there's always this kind of cloud of confusion, and that's why there's many of us in the field who are senior who really sometimes we're like old codgers saying you can't do it that way. But we really do have to hold people's feet to the fire to some degree, because in a young field like this, things can get really out of hand. Real confusion can occur. People can get really misled and do things that aren't efficient. Good thing about neurofeedback is it's a relatively harmless procedure for the most part. And so I thought this would be very important to discuss. Plus, our system is set up in a way so that you can actually locate artifact. And I set up the filters that way because I had already started to become aware that different muscle groups produce different frequencies. I'd done experiments with my own software and my own muscle groups, and I was going like, oh, these muscle groups produce different frequencies. And you can actually get an idea of which muscle group is producing which artifact on your trend screen using our system. And we've got it stratified so that you can. So we're now we could look at higher frequency than we do, but really you'll understand why we have it stratified the way we do, how you can use that stratification to identify which muscle groups are involved to some degree, and that can help you with the client. You can say, well, try relaxing this muscle or that muscle, or they could do biofeedback for those muscles. But I think there's going to be more information about why people tense up different muscle groups. I think there's reasons for it that we don't yet know, but the research on EMG, SEMG is really exploding. I mean, all of even at MIT, there's massive research on it. It's a very hot topic the last 5 years, even 10 years. EMG is a very complex topic. It's almost as complex as EEG. And so just to give us an appreciation for how complex it is and how deep the new research is, and also to help us sort out what we're seeing clinically, can be very helpful. And it'll also help us dispel some of the myths or misconceptions. And you probably won't like some of them. I mean, I have people saying, well, there's EMG in the delta, and I have other people saying, well, gamma is the most valid is very valid, and all the gamma research is good, and I should be training gamma. Well, the fact is that the best research out there that focuses on EMG, they address the entire investigatory community, saying you all need to review your gamma research and you need to discuss how you arrived at your gamma measurements, because right now they are all in deep doubt, and no field likes to hear that. I mean, when Ioannidis told the medical community that 60% of the research was invalid, they just about went into a panic attack as a whole area of research. And then he got invited to every meeting by doctors around the world because they realized, wow, we really have to own up to this. So these paradigm failures occur. It's the same thing when in the 50s when they said sugar was great for you. The problem was all with fat. And it turned out that they were using correlational studies and there were failures in how they measured stuff. And it turns out it's the other way around when you do actual experiments. So just kind of like keeping them straight, we're just going to let's look at the research. Let's discuss it. I mean, I'm not the world's leading expert in EMG, but I got a lot of years studying it, and I think I can present the case pretty well. Let's just kind of go over it.
If you want to, if we're supposed to see your screen, you need to post it.
Yep. Thank you, Rob.
Beautiful. Thank you.
Thanks for the confirmation. Okay. I'm going to rely on a few, half dozen key researchers who've done the leading research in the field. There are these guys in every area who tend to be the dominant researchers. So we're going to look at them. And so let's look at the EMG characteristics. You've heard some of this before. We have some of this posted on YouTube, but I'm going to go to a little bit more depth. The EMG frequency range is now between 0 and 500 hertz. There's one exception, and that's the masseter muscle. That's your chewing jaw muscle. That can be as high as 600 hertz, but most of it's in the 0 to 500 hertz range, particularly across the body. Now, the EMG range is from 0 to 10 millivolts, not microvolts, millivolts. And that's why Herschel Tumum used to always say to me, well, EMG is in millivolt range. He's a PhD in electronics, but I would talk to other people, I won't mention their names, and say, oh no, it's in microvolt range, and they would be adamant about it. I'm going like, I'm sorry, I'm siding with Herschel, who's got a history of engineering accomplishments and a PhD in our field. And Herschel showed me the schematics and, his measurements and everything. It's like, that's science. EMG does have a 0 to 5 hertz local component. So you may have heard Martin say, well, there is some EMG down in delta. And I'll say, well, no, it's not to speak of. In truth, you're going to have harmonics all the way up and all the way down any scale you measure if you create an event. So from that perspective, it's true. And another perspective, motor neurons start firing in the 0 to 5 hertz range, but it's so minuscule in amplitude. It's negligent, and I'm going to show you that. So it's really something that we don't want to focus on. It's a distraction. There's minimal influences in the 2 to 7 hertz range. And Bruner et al. Demonstrated that in sleep research in '96. And they also demonstrated that artifact reduction has a negligible effect on EMG in general, and that has echoed through the research to the present day. He found EMG above 15 hertz contributed 20 to 70% of the power to the signal in general. So, and most of that's on the higher end. And the highest contributions of EMG is in the 26 to 32 range, which is where it really impacts us in EEG and where we really need to focus, not down in the alpha range or the theta range or delta range. And I'll show you that. That's pretty much a waste of time to even look at. EMG increases in on-task conditions. All right, so that has implications for gamma research. And we'll talk about that more in a second. The amplitude is quasi-random in nature depending on fire rates of motor neuron units. That's from 2016, Nizami. But most of that was known all the way going back to the 80s. But he's really making a very strong case for it and what we can do about it. Now this researcher's name is a challenge, Muthu Kumaraswamy et al. 2013. It is well known that the power spectrum of contracting striated muscles measured with surface EMG, which is what you get with EEG sensors, shows a bandwidth of 20 to 300 hertz, and that most of the power is in the lower end of this frequency range. Now, one of the reasons there may be a difference between the 0 to 500 and the 20 to 30 is that 0 to 500 may be putting needles in the muscles, where the 20 to 30 may be more just collecting off of a skin surface sensor. And you get different information doing that, just like you do with EEG. Now, traditionally, low-pass filters were set at 30 hertz. That's what Niedermeyer recommended. That's what all the medical stuff was done. That's the majority of the EEG has been done until, I'd say, the last decade and a half. People started looking really seriously above 60 hertz, above that noise from your wall socket. And they say, oh yeah, there's frequencies up there, because the amplifiers got so good and they were able to put electrodes in people's heads and measure without the muscle tension and say, yes, there are higher frequencies. The problem is that once you start using surface electrodes, you become really overwhelmed by millivolt range EMG when you're trying to measure microvolt range EEG. And that's what calls into question this surface gamma measurement activity that's been done in the research. So if it's almost impossible to filter out EMG completely from the 20 and up frequency range, then how do you know you're really getting gamma? You don't, and that's the answer. And we'll talk about that even more. Now here's the EMG frequency distribution and shift, as I've shown you. Here's 0 to 500. So, and at the top you can see the complex waveform that EMG creates. And you see this on your screen. Tom at Brainmaster used to call it, the caterpillar, the fuzzy caterpillar. He said, if you've got a fuzzy caterpillar, you've got a bad connection. You should get a nice clean line, but this is what you get with EMG, and we'll look at real trend screen samples of it as we go on. But that's a almost chaotic stochastic signal. It's so complex, it's almost chaotic. And there's a reason for that. We'll talk about that. And you can see the frequency range. The majority of it is below 200 hertz, and in fact, even more of it's below 100. And if we really get into it, as they said, it's really in the 20 to 60 hertz range. And here you can see kind of on the left side, a standard distribution. At the bottom is the frequencies, and up on the left side is millivolts, not microvolts. And microvolts is way down here below 1. So we're looking at no fatigue. So this is somebody who's freshly contracting their muscles, and like if they're clenching their jaw or frowning. And then if they do that for too long, fatigue sets in, and then you can see what happens. The frequency distribution shifts down to lower frequencies. So the lower the frequency of your EMG, the more you're in the 15 to 20 hertz range, the more the possibility that's muscle fatigue. But it also creates a problem. Identifying the stratification can sometimes be tricky, because a muscle group will shift its frequency range as it fatigues. So now we get to think, wow, this gets so complicated. Here's tension, muscle group tension from EMG, most likely, and there's that complex waveform you see. And it's not only biphasic, technically it's really triphasic. And this is the masseter likely, and the masseter peak frequency is at 60 hertz around that range. And that's probably what we've got here because it's in the temporal regions. Most of the masseter muscle, majority and the most intense part of it, shows up at the temporal region, temporalis muscles. And it's below the temporalis, but it comes up through that area. Signals travel, something that we have to keep in mind. And this is AC noise. Now, if you're using an EMG equipment like with Thought Tech, really high-end biofeedback equipment, they what we call rectify it. They take it from being a sine wave up and down, and they turn it into more of like a DC wave. And there's a way you can do that with diodes and rectification methods. And we don't need to get into that. And you often measure it as root mean square instead of peak to peak, like with EEG. We don't need to get into that. If you're in biofeedback and you get certified, you have to learn that stuff, but not if you're in EEG usually. Now here's a yellow line. You know this is high beta, and look how high that is. That's up in the 40 hertz range, the 35 hertz range. The real alpha range is around 5 or 6 microvolts, and there's a 1 to 2 microvolt standard deviation. So the minute you're up, the minute you're up over 7 or 8 microvolts, you're probably pretty contaminated with EMG. The statistical analyses I've done, with n-size numbers in the tens of thousands, if you analyze it really, you can see in the variance and playing with it and doing modeling that a lot of all of that is muscle tension, and that's confirmed by even more sophisticated analysis than I'm doing, and I'll show you some of that. So whenever you see that yellow line up there over 8 or 10 microvolts, you know that's not real. Now what's interesting here is notice that the red line is down here. Now in the BrainMaster software that I used, and even and I use that the most, but I also use Thought Tech, but you generally see the beta and the high beta move together, not always, but that's because different software developers use different frequency ranges to capture beta, high beta, and EMG. Some of them don't even put EMG in. So sometimes these generally move together, but sometimes they don't, and that's an indicator that is coming from a specific muscle group. So this is likely 20 to 40 hertz with a mild 15 to 20 subharmonics, because notice this beta is at 15 microvolts, so it's way higher than it should be. So there's a subharmonic. Now, what do I mean by that? And we can see here it says 20 on the EMG. Well, that means it's in the 40 to 50 hertz range or higher. So our EMG measures pick up the higher end between like 40 and up to 60. And when we have low pass filters there, where we chop out the 60 hertz signal so it doesn't get contaminated. But this is telling us that we've got a lot up there in the 40 range. So that's why I say it's probably in the 20 to 40 range, and we're getting a subharmonic. So we'll explain that in a short bit. Now, here are the muscle groups. Goncharova et al. Is one of the best studies done on this. An excellent study. And you can see the frontalis muscle is between 20 and 30 hertz, temporalis between 40 and 80. So your frontalis muscles will tend to show up a lot in the high beta, primarily. Temporalis muscles, more in the temporal lobes, will tend to show up more in the EMG reading on your software. Masseter's peak frequency is 50 to 60. That would show up in the EMG more. But remember, these all have subharmonics. We'll get into that. In the back, when people talk about muscle tension in the back, they're stretching those muscles and they're tired. That's 100 hertz. Well, we don't even measure that. How do we get that? Well, we measure it in our software through the subharmonics. Extraocular trapezius, shoulder tension. That shows up more in the 100 hertz. How do we measure that again? We capture it through the subharmonic in our filters. Extraoculars at 65. So those are the different frequency ranges, and this will be posted. You can go up and look at this again on YouTube. And then we can see the muscle groups here. Excuse my phone, I forgot to turn it off. We can see here's the frontalis. You can see that right there. And then over here around the ears here is the temporalis, this whole range, F7, T3, T5 starts to get into that. And then you can see the temporalis below that is the masseter. You can see that down there. And that feeds into the same same regions, as you can see, where it all anchors together on the scalp. And so electrical activities move across these muscle areas, but also these muscles all tend to co-contract to some degree, and they do it differently in each person, and based on scalp size and history and all these other things. So it's not too easy to isolate, but you get a pretty good idea. Yeah, the stronger the contractions, the more you can oftentimes localize them. Now here's EMG. The EMG here is occurring in the trapezius most likely. You can see that EMG there. That's got a 100 hertz with subharmonics in the 50 hertz, 33 hertz, 25 hertz, 20 hertz, and 16 hertz. So if you're tensing your shoulder muscles, you're going to produce frequencies that show up across your beta range in all these frequencies, beta, high beta, right? And up into gamma, and then what we call EMG on our software. We don't call it gamma, we call it EMG, because that's what the research tells us. So trapezius muscle will just wipe out everything, make everything go high, because it's in the millivolt range and your EEG's in the microvolt range. So here might be what my trapezius looks like, high beta and beta, 100 hertz. But we're not getting anything in the 40 hertz range. Interesting. So you see it gets kind of complicated. Now, here's a frown artifact, 30 hertz, and potential subharmonics in 15 and 10, possibly down into alpha if they're tensing, they're frowning enough and hard enough. The problem is those muscles can contract in younger people, and you won't see the furrows in the brow, but there'll be a lot of tension in those muscles, and you won't be sure where it's coming from. So Rob has this thing where he has people go through and clench their jaw and frown and do different things, and he shows the clients, the different types of things they can do to mess up the signal. And that's actually a really good clinical practice, because as a clinician, you can actually see what their unique signature is in each frequency band with our software. There's tense your forehead. Okay, now clench your jaw. Okay, move your head backward and forward, and you can see which area produces the most muscle tension. All right, let's jump to, now here's a trapezius on the BrainMaster software. And here's a nice, I just had this kicking around and I was kind of in a hurry, so I pulled this and threw it up there. It was very, very good example. You can see the morphology here of a nice regular EEG. But you can see they're starting to get those high peaks that you start to see in the lower frequencies. It may be in high alpha amplitudes and low beta amplitudes, and then you transition into this EMG. And you see it's not quite as tight right? And not as spiky as like maybe jaw tension would be, or temporalis muscle. And you can see here, well, the peak looks like it's in the low beta range at this point. So that's a subharmonic, right? It's a subharmonic. So Goncharova, if that is how you pronounce his name, and I'm not an expert in names around the world, but he actually measured people's EMG amplitudes, and he set up a system so you could gauge whether your contraction level was at a 15% rate, a 30% rate, a 70% rate, or a 100% rate. Elegantly done research. And he did it at all locations in the EEG. It's one of the best research projects on this I've ever seen. And I forget who sent it to me. It may have been Michael. It's really just a wonderful thing, because you can see the lower line is 15%, the next line is 30, and then the next line is 70, and next is 100. I guess this is base rate at the bottom. So you have base rate, 15, 30, 70, and 100. And you can see in terms of microvolts, 0 to 100 microvolts, how much artifact that can produce. It's pretty impressive. And you can see the majority of the artifact of concern is really in the frequency range is mentioned. Now, if we look at the distribution of that, and he even did that, which I think is really cool. Here we have monopolar, which is what we use. In other words, when you're doing QEG with us, you're usually doing monopolar. In some of the softwares, other softwares, you can do Laplacian montages and all kinds of other montages, which is great if you're doing research. I don't find them that useful for clinical neurofeedback. I would if I was a neurologist, however. But neurofeedback, I think our monopolar works more than well enough for what we're doing. Now, this is showing you a 15% contraction range in the 1 to 200 hertz range. So they're comparing frontalis left and temporalis right. Okay, so they got frontalis and temporalis, and here's the frontalis here, left-sided, and temporalis right-sided. And the 0 is means that that's baseline, and then p less than 0.01 would be like a blue, no, I mean would be red, and then p less than 0.00001 would be down here in the dark blue, and that would be really low and insignificant. No, actually, it's the other way around. I'm confusing. It's the other way around. It'd be the other way around. Sorry. That would be really insignificant, and then as we get more significance, it would be turning red. You can see here that there's really, at this range, there's no significance in the delta whatsoever for the most part range, which is why I always say it's not likely going to show up on a map as of anything, and these people would have to be really working hard, tensing profoundly and consistently, almost beyond the point of human endurance, to produce a significant signal. You know, you'd have to be up in the 70 to 100 hertz range to get anything up here. And so you can see this is slowly getting more and more red in the front. We're around 18 hertz. You see, even though SMR is showing up in Laplacian, but it's not showing up here. So when you're using monopolar, you're not really seeing much at a kind of a general range, elevated range, till about 22 hertz, right? And you would see it much more clear, maybe more like down like this at 22 hertz if you were in the 75 hertz range or something like that. But just at a moderate EMG that typical person might come in with, that's not too high, you really don't get much until you get up in the 22 hertz range. Interestingly enough, that agrees with Witham et al.'s research, which was based on this research and done almost 10 years later. and we'll talk about him in a second. So distribution characteristics, EMG power levels in general peak at 30 hertz based on this research. Weak contractions, 15%, generate mild increases in 15 to 20. Anything below that is very mild, is in the Witham range, which means that below 20 hertz is mostly real EEG. Peak frequencies in the 20 and 25 hertz range shift to 35 to 38. The more they tensed up, the more these ranges shifted up. Now, once they start to fatigue, they'll shift back down again and actually shift below maybe 20, 25 hertz. Temporalis has the strongest impact in the central. So when you're getting stuff noise in CZ, C3, C4, which you don't often get, but you do, it's probably the temporalis muscles. Now they're saying peripheral leads are the highest, and that's just saying FP1, FP2, F7, F8, all around back to O1, O2. Frontalis and temporalis co-contract to a fair degree. So whether it's the temporalis or the front of the forehead, they're going to both produce at the same time, and that's going to produce different frequency ranges. And those ranges are going to shift with the intensity of the contractions and or with ongoing fatigue. So suddenly we've got a moving target. It's constantly shifting, and that's what they say in the literature. Alpha dominant frequency decreases during contraction, but increases in the temporal regions. Amplitude in the 15 to 20 hertz range and parietal occipital region decreases. So the alpha dominant frequency actually goes down to the degree that the temporalis muscles. So that's an interesting phenomenon that could have some interesting ramifications for norms in brain maps and databases. Were they looking enough at temporalis contractions, and did they account for the loss in alpha dominant frequency and changes in power? I doubt they did. This is very contemporary research. That's going to affect the validity and reliability of the old databases, and they're not going to want to talk about it. Amplitude in the 15 to 20 hertz range in parietal and occipital decreases. Back beta in the 15 to 20 hertz range can decrease in the back. So that can also affect norms too. So let's just quickly get into harmonic distortion. And I won't get into this too much, but just to kind of give you an idea again of how everything gets distorted with EMG and how complex the whole topic is. So here's a sine wave, and that might be one motor neuron. But then you get another motor neuron, and they don't always fire at the same rate. We'll show you that in a minute. And then another, and then another. And you can see that you get all these different waves beating together. And what happens is they produce different phases. They're out of phase, and hopefully you remember that from my other lectures. And those phase cancellations shift and alter the shape of the wave. So it goes from a sine wave to maybe something more like a square or a sawtooth wave. So let's look at that. Now, when these other waves come in, they also create subharmonics. And every wave in itself can generate subharmonics. And how we define a subharmonic is different than a harmonic. With a subharmonic, you divide the frequency of the wave, let's say it's 20 hertz, by 1/2, that would be 10. And then 20 hertz by 1/3, and then 20 hertz by 1/4, which would be 1/5. But we don't go down that far, right? The more you divide those subharmonics, the more the energy dissipates, and then it ceases to have meaning. So here's a motor unit wave form right here. And then we get here, we get another strand. Here's your muscle fibers, and they fire at different rates and add in at different times and different intensities. And then you get a total waveform that's triphasic, fundamentally in nature, but looks like a mess when you see it on an EEG screen. And if we really get it, if we can attempt to make it stationary instead of constantly moving, and these waves are not stationary because of their complexity. EEG can be somewhat stationary, but not EMG. We would theoretically get a waveform that looks something like this. And so you can measure amplitude, duration, complexity, and look at it from. That's what they're doing in EMG research now, and they call it a MUAP unit. So here's the motor unit firing, and you get a couple firing, and then they fire more frequently here. So these two motor units are firing, and then they fire more frequently and with more intensity, and then a third one jumps in. And that can all take place in a very short period of a second or two as you begin to move your muscle. The outcome is this resultant stochastic signal with complex harmonies. So what we have here is some modern experimental techniques to quote unquote denoise the wave, get rid of the harmonic content, and try to get down to the fundamental waveforms. And the yellow would be all that harmonic content and noise, and there's your fundamental. And I kind of give you an idea of how much of what you're seeing when you see all this mushy mess, the fuzzy caterpillar on your trend screen. Underneath it is kind of some sinusoids that are complex triphasic. These authors took that signal and progressively decomposed it so you can see the different components that are in here. So you've got a lot of different motor units contributing different components depending on where you place the sensor and how much of an area they're gathering in. So your EEG sensors are gathering information from a pretty big area on the scalp. That's bringing in a lot of millivolt level energy, and you're trying to collect microvolts. Here's another visual way of looking at subharmonics. Here's a 55 hertz. This is very close to the subharmonic output of a 60 hertz dirty electrical noise from your wall socket. And you can see these big lines are subharmonics. Interestingly enough, these little lines are reflected harmonics from the fact that it's a limited sampling range, and you get what they call Nyquist reflections, and we don't need to get into that stuff. But but it shows you how dirty the signal can get depending upon the quality, the sampling rate, and the quality of the range you're taking in. All those things affect it. So let's get a little more visual about this. Here's a sine wave. Let's say these are a couple of motor units. This is just what a sawtooth wave theoretically in blue would look like, and then we have these red and purple motor units, and then the more of them that kick in, look how the disparity in their phase relationships and their harmonic content start to shift the waveform, and you can do this mathematically. You can look at the sine and cosine and add the harmonics. And as you add the harmonics, look at how the wave shape. It starts to look like a sawtooth wave. That creates a noisy mess. Your sinusoids can also add up as you add content, and you start to see square wave, which is very noisy as well. And as we said, muscle fatigue. Here's a muscle fatigue. There's an initial EMG. The signal starts to degrade, less and less firing. The frequency drops down, less firing, the frequency drops further. And so it's a shifting pattern. Now, on your brain map, you might see T3, T4, and high beta, especially if it's localized. Odds are, 90 to 1, it's EMG, even more than that, actually. This is probably masseter with a 40 to 60 hertz peak. So it'd be somewhere in the range of these two lines right here. And then as we go over to beta, we notice that same area is elevated. Maybe not in T3, that could be fatiguing over there, or maybe not as much firing. And then we could see that would be in the range where the red lines are. So that would be the subharmonic. And the subharmonics would be of 40 to 60. The main frequency would be 50. The subharmonics would calculate as 25 hertz at 16.6 hertz. So there's high beta and beta right there. We might even get a little bit of 12 to 15 and 10. And oh, look, there's a little elevated 14 there. T4 there. So that might be a subharmonic as well. Now these delta and thetas, they're not likely anything to do, especially at 2 and 3 standard deviations. The odds of them having anything to do this are like, 99.9999 to 1 that there would be any content here driving this here. So we talked about this one already. Let's jump to removing EMG. There is no single technique that can suppress all muscle artifacts, nor does there exist a single data feature that allows easy discrimination of brain and muscle activity. Small muscle artifacts can pass through most screening and remain present in so-called artifact-free recordings, 2013. The confound of EEG and EMG makes identification of EEG above 26 hertz very difficult. That's all the best research. And these people are challenging the people doing gamma, literally in the field saying, you need to check this out. And I often cite this guy all the time. I've sent this to the other database people. They don't want to talk to it. It's crickets. But sooner or later, we're going to have to deal with it. Frequencies above 20 hertz are contaminated by EMG right there. And this came from 2007. So this was later on. Here's Witham's, one of his charts here showing pre and post neuromuscular blockade. So more or less they injected the person completely, all their muscles with curare to make all their muscles flaccid. And they did a recording before the injection and the blockade and a recording after, and the A is before and the B is after. They used 115 channels. It was pretty thorough. In the 20 to 30 hertz range, 84% of the EMG power. That agreed with the previous author. So most of your EMG in your EEG is going to be in the 20 to 30 hertz range on average. So now maybe you get why I say don't trust high beta. High beta is not there. It's mostly just illusion, and why I don't promote looking at gamma. A 200-fold pre-post difference in EMG in the frontalis and temporalis locations. The CZ showed the least contamination. It was only a 6-fold. Contamination below 20 hertz was very low. For most people, relaxed. That's probably in the 15 hertz range of that Gonrachova was researching, because these guys talk to each other and know each other and riff off each other's research. EMG increased under task conditions. Witham found the same thing. Well, that would completely confuse you. You didn't know that, and you thought you were getting EMG, particularly with our grade equipment. I mean, come on. We're not using laboratory grade equipment and software. I mean, not the kind that they use for really high level research. So I just did a little quick test with our equipment, just for fun. The EMG baseline when I was there was 2.2. The delta was about 7, and the beta was about 3.6. A little bit low. I'm an old guy. Brain's probably shrinking at 70 years of age. But given that's the case, when I tensed up my muscles really hard, look what happened. This didn't go up high. You know why? Because when I tensed my muscles really hard, it kicked off the high EMG filters, and they just cut out the EEG. So to get this to record my EMG, I had to clench my jaw and keep it in the range on here looking at the EMG. I had to keep it between 4 and 10 hertz, because once I get above 10, it clips more and more of the EEG out. So our system blocks, based on EMG stratification. That's the technique we use. I'm revealing it to you. We're blocking out the high-end EMG, because that what really interferes with your neurofeedback. and with valid mapping info. So when I kept it in that range, you can see I was able to get it up to 810. Now up here, I'm probably at 50%. Down here, I'm probably more like 30%. So you can see that on our software, how that reacts. I would encourage all of you to hook your sensors up at the CZ, because that's where temporalis is most affected. Start clenching your jaw, try to keep it in and play with it and see what you get. I got a 9% increase in delta and a 28% increase in beta over this range, and you can look at the delta. Even live, there's very little contribution in alpha, theta, and delta. It's almost none. So these are the facts. And in this one, delta drops as ENG increases. So arousal increases. It makes sense that people would become more alert. Delta would drop. Beta artifact at 15 to 20 hertz over here. No shift in delta, theta, or alpha. So again, I'm just showing you, even in our software, it's consistent with the research literature. This is likely frontal activation. Okay, on the left side, because it's a solid line. It's likely F3, F4, because that's where it says. It's in the 20 to 30 hertz range. I know that because of this. That tells me it's probably frontalis muscle. There's a relaxation of the frontalis muscle. And the 15 to 20 is pretty steady. Look at that beta dropping down. I'm speeding things up. We're getting towards the end. Here's a baseline temporalis, probably, because when the person tenses up, we're getting 10 to 12 microvolt peaks in the 40 to 80 hertz range. How do I know? Because we measure at the bottom of the 40 hertz into the 50, and we're getting 20 to 30 harmonics, which would affect this, but there would be very mild 15 to 20 harmonics, and you can see that's a much milder effect, and that's 1/3 F. So really looking at the software, you can triangulate where the likelihood that the muscle tension is coming from, and eventually we'll include this in the software. We just need a little more data and a little more time before we put it in there, but you'll be able to even have an image on the software that says this is the muscle group. We'll have a little head with little muscles on it, and you'll be able to see them light up, see which muscle group is producing it. Here's a baseline of somebody with a bad back on one day, 6.5 volts on their EEG. Their back is hurting them. And look what we've got. This is probably the back radiating in up, the back straight up into the trapezius and triggering trapezius tension. And so we're getting 10 microvolts at 20 hertz and 30 to 40 hertz, not 15 to 20. So this is likely trapezius or lower down in the neck and back. So that's how somebody's bad back can distort what you're doing. Here's jaw EMG at central region. Dominant range is 20 to 30 hertz, subharmonics at 15 to 20. Notice we're not getting a huge amount. There is quite a difference between the two, but we're still over 10 hertz on the subharmonics at 15 to 20. So that's more likely temporomandibular activity. And finally, we have busy mind. Notice there's very little EMG. That's because most of the people are keeping themselves calm by keeping a busy mind and suppressing input from the amygdala. This is one of several strategies that show up on your trend screen, different ways people manage their social distress. And it shows up if this alpha goes down, eventually you'll start to see this beta coming up. Yeah, now we are fairly high. We're at 8, so we know that's not real beta. But notice it's in the 15 to 20 hertz range. Okay, so almost out of time. Just wanted to go over that, and hopefully that will help you all get better ideas about what you're dealing with. Any comments before we
Well, I've got two, Richard, really quick. One is I imagine so on the mapping system, when you see artifact detected in delta on the map, that's probably more likely to be eye movement than muscle tension. Would that be a correct assumption?
Uh-huh. Yep. That would be the
Yep.
correct
And
assumption.
then when you're looking at the gamma research by people like Bonstetter and Tom Kalora, because they've covered that pretty extensively, um, I imagine the negative mood versus positive mood is that they're picking up in part is related to the muscular structure around the face when people are happy about something and smiling versus frowning at something that they dislike.
Um, I would imagine we'd have to conclude that because they did not address that in the research and they did not show how they excluded the muscle artifact. And Tom is more than capable of doing that. And could
Right.
probably discuss this in even better detail than I can because he's a signal processing expert. He's ex-Bell
Right.
Labs. So, I mean, he certainly can address it for sure. He technically knows more about it than I do.
Those are just two quick comments from me based on the talk and what we've discussed here in other webinars, but others may have a couple of questions.
Yeah, well, I've unmuted everybody if anybody has a closing question or two. I know it's a lot to chew on, especially it's very disheartening to all those people getting excited about gamma research, but we really need to be honest about this. That's what science is about, and it's exciting, all these ideas and everything. And, you know, Richie Davidson, you know, hopefully he's addressed this in his research with the monks.
I don't know if you just, oh, there you go. You dropped out for a second.
Okay. I said, hopefully Richie Davidson has addressed this in his research with the monks. And I mean, these muscle tensions in beta distort S. Loretta. And that's why I say, well, yes, S. Loretta is 100% accurate, but it's certainly not going to be in the beta ranges, especially if it's anything over 20 hertz. And you can see it's so easy for muscle artifact to disrupt S. Loretta. And even the scalp shape is critical. Thatcher at least has addressed that to a fair amount. But, you know, there's a lot of questions that still have to be dealt with all of this when you're doing. So that's the problem with doing some of the really high-end neurofeedback work is it's relying on information that's not reliable. That's why I try to keep it simple, standard neurofeedback, and not make too many assumptions, and follow the research carefully. And let's be kind of realistic about what we're doing.
I have a quick comment. Maybe we can talk about this next time because we're not actually having time now. But I've looked into the research of cross-frequency coupling and phase amplitude coupling, and that's really made a big difference in how I do neurofeedback.
It has. Well, that would be very interesting to hear, Lisa.
Okay. Yeah, maybe we'll talk about it just as a group next time.
Yeah, and we have to be careful with coupling with phase, and we can talk about that. In the higher frequencies, when you have beta, that's going to tend to produce out of phase measurements in the EEG. So it's a very pertinent topic as well. I didn't even bring that up, but that is an important thing to think about too. All righty, everybody. Well, we're just past the top of the hour, and we'll post this, and you can review it again at your leisure in a couple of days when we get it up there. And hopefully this has opened your eyes and given you something to think about, your considerations when training. Overall, our filter system takes care of most of this for you, but you don't get fooled when you see that beta, any of it going above 8 or 10 microvolts. Just think this is probably not real.
Well, that was an excellent talk, Richard. I really appreciate it. I learned a lot. I think it was a good review of some of the things we see so typically. So hopefully people will have questions. If people have questions specific about the presentation, feel free to email them to us so Richard can prepare some responses, you know, more readily. We'll take those on Friday.
Yeah, be great.
Thanks again, Richard. That was great. Perfect.
All right, everybody. Have a great week.
Yep. See you Friday.